with the board. So I will just, because I want at the beginning to give you a little bit of an overview, and when we get to the proof I want to do, I will switch to the board, okay? So in the first two lectures, I gave some background about some ancient solutions. We talked about ancient solutions of the heat equation and the semi-linear heat equation. And as I told you already, the reason we started studying these ancient solutions is because what we had in mind was to study ancient solutions of geometric flows. So what I would like to do in my last two lectures is talk a little bit about this project of ours, but I will concentrate in two simpler flows. The curve shortening flow, which is the simple case of the mean curvature flow, and the 2D Ricci flow, which is, okay, it's one dimension higher than the 3D Ricci flow that we had in mind, although it's a little different. Okay, so now I guess yesterday you had the computer session and you studied some solutions to the curve shortening flow, is it right? Okay, which is the simplest geometric flow. I will introduce it a little bit later. And it's the evolution of a curve on the plane by its curvature. And Robin also talked about this in your review session. So, and this is the simplest example of, as we say, of an extrinsic geometric flow. And what does it mean, extrinsic? It means that we study the evolution of hypersurfaces that are embedded in Rn, let's say Rn plus 1 if you take an n-dimensional hypersurface. Okay, so for example, the curve is embedded on the plane, two-dimensional surface is embedded in R3, etc. And some other examples is the mean curve flow, which is the higher D analog of the curve shortening flow. And this is the evolution of a hypersurfaces by its mean curvature, which is the sum of the principal curvatures. This is only for the students that have done some geometry. Gauss curvature flow, it's a beautiful flow, it's a fully nonlinear equation, is the evolution of a hypersurface by its Gaussian curvature, and other flows. And now these are extrinsic, so these are geometric flows on hypersurfaces. You evolve again a hypersurface by some sort of curvature. And intrinsic geometric flows means that you don't change the manifold. So you have a manifold, you have a metric on a manifold, and the manifold is the same. What you change is the metric, okay? And the examples for such flows is the so-called Ricci flow and the Yamabe flow. And today in your problem session, you will learn a little bit more about the Ricci flow. Now, again, in these last two lectures, we will concentrate mostly on curve shortening flow and on the Ricci flow. And don't worry, it's going to be very little geometry because very soon we will switch to PDE. Okay. By the way, I consider myself an analyst. I'm a PDE person, so I'm studying these flows. I mean, okay, the geometry, of course, is very important, but the PDE is important too. Okay. Now, you don't need to read all this. We have talked about it already. So in these geometric PDEs, and in all PDEs, as we talked already, some of the most important questions is understanding the singularity. So what does it mean in a geometric PDE? A singularity means that the curvature, usually, some sort of curvature, it could be the curvature of a curve, one object, or the Ricci curvature, the mean curvature, whatever, the Gauss curvature, blows up. All right, so something happens. And And right? And we had a very simple example last week, where 2 days ago, okay, where we have had it last week too, where it was a semi-linear heat equation, du dt equals Laplacian of u plus u to the p, and we saw exactly what it means for a singularity to happen, and I made the connection there with the flows. So this is what really happens, like some sort of curvature blows up, like in that PDE we studied. And of course, that PDE, it's simple PDE, but when you have a very complicated PDE or a system of PDEs, it's much harder to analyze, okay? And to analyze the singularities, what did we do last class? We concentrated by doing this rescaling, remember, at the singularity. So you introduced this blowing up procedure, and then we took a limit. That's exactly what we do in the geometric equations. And after that, as we discussed, you end up with after you take the limit, we already discussed that you end up with a solution, since it's a parabolic equation, a solution that have existed for all time, an ancient solution. So we know this now because we did this specific example. And let me repeat, an ancient solution u of x and t to a parabolic equation, no matter what it is a solution that is defined for all time starting of minus infinity. And by parabolic equation, I mean heat equation and analogs, okay? We talk about it. And as I said last time, that last class, if the solution exists all the way up to plus infinity, it's still ancient, but we call them also eternal. And okay, I don't want to say anything else about that. Now, so in these geometric flows, usually there are some typical solutions that they appear as ancient solutions. And these are very important objects because usually complicated singularities in different points look like those simpler models of solutions. And these simpler models of solutions are often or usually self-similar. What does this really mean, self-similar? Means that they are solutions, they are special solutions that they move, they change by a very specific way. And for example, one typical example of self-similar solution is shrinking spheres. In the case of the curve shortening flow, is a shrinking curve. In the case of higher dimensional flows are spheres that they shrink, okay? They change this. But you know what happens in the case of the sphere? You change, as you move, you change the scale, right? The size, but you don't change the shape. So this is a special solution. It moves by shrinking. That's how it changes. It doesn't change the steps, okay? So this we call the shrinkers. The same thing for cylinders, right? What is a cylinder? You all know what it's a cylinder. It's a sphere across a line, all right? And a sphere, in some of a cylinder in some of these flows will shrink. Most of the flows will shrink, some flows will expand, so because the sphere shrinks, okay? The line usually doesn't move because it doesn't have any curvature, but the sphere shrinks. And again, when the cylinder shrinks, the shape does not change, the size changes. So this is, as we say, a shrinker or an expander. But there are other so these are very basic, but there are other more complicated special solutions, we will call them solitons, that they look like this. This is like so they're rotationally symmetric, so if you view them as hypersurfaces, they're rotationally symmetric, but, and they're compact in one end, and here this part extends all the way to infinity. So this is one, and the other one, this is a different one. I just put them back to back because I want to show you something else. Okay, so one is compact here, extending all the way to infinity like a cylinder. Geometrically looks like a cylinder, and the other one is the same, it's just a reflection. And these sometimes, again, do not change the shape, but they just shrink, or they may expand, or they translate. And what does this mean? There's nothing changes. They don't shrink, they don't expand, they just move by going up and down. All right? So these are very typical special solutions that we see as self-similar solutions. Now, these ones are particular examples also of ancient solutions, in most of the cases at least. For example, the spheres that they shrink, if you go back to minus infinity, the diameter of the sphere, the radius, increases all the way to infinity. They have existed forever, right? Now, going down, going forward, they don't exist all the way to plus infinity. They will, because they are compact at any given time, they will just eventually contract to a point in finite time, depending on the flow, but just a general idea. The same thing in the cylinder. Let's say that you have shrinking cylinders. If you go backwards in time, the diameter of the sphere, because this is just a sphere, right? The diameter of the cylinder, it goes to plus infinity, but it exists all the time. Forwards in time, and if, let's say, you imagine something like that, that translates, going forward in time, you translate up, okay, you can translate down as much as you want. So it's that one, it's an eternal solution if it translates, because it as you go to minus infinity, it goes all the way down, you go to plus infinity, it goes all the way to up. And these usually are the building blocks of our singularities, and the building blocks, as we are going to see, of our eternal solutions or our ancient solutions, our more complicated ancient solutions. Okay? All right. Now, but on the other hand, when we study singularities, and that appears in really most of the flows. Okay, if you take away this circle, okay, then it becomes in 1D. Right? Let's take this. This means that you have a rotation symmetric hypersurface. But if you take this circle away, you can view it also as a curve, right? And so there will be 1D problem, like curve shortening flow, but it's higher D, it's rotational symmetric. And so this is a very typical case of ancient solution. So this is the behavior, the typical behavior of an ancient compact solution, and this is very close to minus infinity. Of course, the scale here, right, this is very long, very close to minus infinity, but I don't have so much space to make it so long, all right? And now this one is not self-similar, it's not very, it doesn't move by shrinking, expanding, or translating, but it's a combination of things. And very typically, near the tips, you see, that's why I put them before back to back, you know, you see something like that. So really, in these ancient solutions, very close to minus infinity, here you see a translating soliton, or it could be even a shrinking soliton. And on the other side, you see something like that. And in the middle, typically, you see a very long cylinder. Okay? And so these are, they appear all the time. So for the case of the in the curve shortening flow, we are going to see is the so-called Engenet ovals. For the case of the mean curvature flow, only for the students that they are familiar, we have the so-called Bryan-White solutions. And for the case of the 2D Ricci flow, King solutions, 3D Ricci flow, the Perelman solutions that we will talk about. Okay, so they appear all the time. And okay, sometimes we have also things like that. This appear in the so-called Yamabe flow. So you have spheres glued by very short necks. And these are kind of irregular examples. For example, here the curvature, these things are like, they look very round, right? The curvature is always positive here. But here, at least, but here the curvature, you see, you have some negative curvature, some positive curvature. So these are not typical examples. They're kind of weird examples, but these are very typical examples. And knowing that these are the only ones are very important, because it makes our life easier when we classify singularities. Okay. So, About 10 years ago, we started with my collaborators back then with Richard Hamilton and Natasha Sessom, who is also around, not today, but tomorrow will be back, to study these ancient solutions, because what we had in mind is a conjecture on the Ricci flow, which I will talk tomorrow, but just for the students that are familiar, due to Perelman on classifying the ancient solutions of the 3D Ricci flow. And that was so complicated that we soon realized that we had to go back and start with a simple possible case. So we started with a curve shortening flow, which is the simple possible case of an evolutionary equation, and we move forward. And actually, only now we think we are able to finish what we started after 10 years. So I want to tell you a little bit, that's a story just to show you that in math you have to be very patient and have a vision and a program, and etc. Okay, and so so we started a program which we want to provide Liouville type results, which as we saw for the heat equation, uniqueness results for ancient solutions. Okay, so here is an equation. Here I'm giving you an ancient solutions. How many do I have? And as we saw from the heat equation, if you don't put any conditions, you have too many. You have the harmonic polynomials, etc. But if we put some natural conditions, and for example, some bounded curvature condition, or in some other geometric condition that I don't want to specify so much, convexity, for example, etc., then we reduce the class and we are able to classify. If we remove those conditions, we have many more. Sometimes understanding this many more is interesting because these many more also appear as singularities. Sometimes it's not so interesting because they don't appear as singularities, so it doesn't really help us in our ultimate goal, which is understanding the singularities. Okay? So the idea again is to provide uniqueness result for ancient solutions to these geometric equations under some natural conditions, which of course makes this possible. Okay, and as I said, okay, this is what I said, and as I said, we soon realized that we could not do 3D Ricci flow. Then we said, okay, let's do 2D Ricci flow, which was easier. We realized we couldn't do 2D Ricci flow, so I said, okay, let's do 1D. There's no 1D Ricci flow, but actually it turns out, and it's very strange for the students against that they're more familiar, that mean curvature flow, 1D mean curvature is curve shortening flow, and Ricci flow, they are two very different flows. The one is extrinsic, the other one is intrinsic. They turned out actually to have quite similar properties. So we said, okay, curve shortening flow. And it turned out that that one was easy actually. Okay, so for the rest of my lecture today, I would like to concentrate on the curve shortening flow. And again, I will start with some background, which I will give you here, and then when it comes, state the result, and then I will come to the board and talk to you about the proof. All right? Okay. And Robin talked to you a little bit about what it is, the curve shortening flow. It's the evolution of a curve. The curve is the red part, and we can view it as the boundary of the yellow part on the plane. We're not going to embed it anywhere, it's just embedded on the plane by its curvature. And even in multivariable calculus, we define the curvature, right? And we do move, and sometimes you can view curves that move by the curvature. This is a simple. Now, it turns out, so you evolve, but how do you evolve it by the curvature? Always in a normal direction. So we evolve, each point, you evolve by, right? in the normal direction. What does it mean? Perpendicularly to the tangent vector, to the curve at a particular point. And now the only question is, do we move? How do we move? Do we move? Does this point move inwards or outwards? Now it turns out that this has to move like this, inward, because if you sit here, so you have some it goes like, it's like okay, in some respect, if you view it like that, it's convex. Now this one has to move outward. The concavity changes. Now if you have something convex, which we will switch to later, always will move inwards. So why, right? It moves. So it moves in, so for the convex. And this one will start moving inward and this outward until the shape changes. After the shape changes and becomes convex, for example, then of course it has to start and moving inward, right? And so why do we need this orientation? Because if, let's say, you have a convex curve, if you move outward, you can say, okay, I define a flow that it moves outward. But then it turns out that when you write it as a PDE, which is almost like a heat equation, you pick up the wrong sign. You remember, what is the heat equation? du dt equals uxx. And that the fact that it's plus uxx is very important. So if you change the orientation, you put minus, it's really bad. It will develop immediate, it loses all the goods characteristic. Okay, so the orientation is very important and has to do with how it moves. Now, this flow has a very remarkable property, which was a known result by Gratian, which says that even if you start with something which is, okay, this is not so complicated, but a closed curve, it has to be closed, so compact, right? If you start with any closed curve that it's embedded on R2, the fact that it's closed and embedded, and you start with, tells you that before eventually will disappear, but at some time it will become convex. So you give, embeddedness, only the fact that it's embedded, right, and just this flow tells you that something like that at a later stage will be like that. Why? Because you see, this will move outward, this will move inward, so eventually you will get convex. It's not an obvious result at all, and so eventually will become convex. Okay, so this is very remarkable property, and no other geometric flow has this property, that you start with something in higher G. So this is the only flow, this is an ideal flow that has this property. This is a beautiful result by Gratian. So you start with any closed curve, it becomes convex. Actually, it becomes strictly convex. Once it's convex, strictly convex. And then there is an older result by Gates, I think this is 86, it's wrong, no, 96, by Gates and Hamilton, that says once you have a convex curve, which will start moving only inward, so it will only be shrinking. In finite time, it will contract to a point, okay? And it contracts, you talk about it, as it contracts, it becomes more and more circular. So, right, you will contract. So what does this mean, contract? It means that eventually the length of the curve will be going to 0. The curvature, what is the curvature of the circle of radius r? 1 over r. So as the length goes to 0, the curvature goes to infinity. But if you rescale, like we did in our last lecture, to have constant curvature, at the limit you see a circle. So it becomes more and more circular. And this is the result of Gates and Hamilton. Convex curves they shrink in finite time and they become very circular. Non-convex become convex, so eventually they become circular. Okay? All right. Now again, if you take any singularity, which means, and you rescale around the singularity, you will end up with an ancient solution. And Okay, now here we understand quite well the singularity. So studying the ancient solutions, as you know, it's not as important as in other flows where we don't understand the singularities, but our point was to develop techniques, all right? Okay, so, but before I do the ancient solutions, let me talk a little bit about some equations. Okay, so Robin gave you some equations also. As I told you, we will soon switch to PDE. So, and PDE familiar to us. This is similar to what we studied last time. So let me give you some equations. So equations. In all these geometric flows, so it's very important. The first thing we do when we start computing is we compute the evolution of the curvature, right? So the definition of the geometric flow, which I gave you and you also studied in your review session, is you move a point by curvature, okay? That doesn't tell you how the curvature itself changes, okay? So the first thing that we compute is how the curvature changes. And so so kappa is the curvature, and our equation here is that the curvature obeys this semi-linear, okay, heat equation. Okay. Now this is a little misleading. It's not as easy as we think, because S is arc length. And as we know, if you have the arc length of the curve and the curve is changing, the curvature is changing, the arc length is changing. So this is not an independent variable depending on time, depending on space. So this is a geometric quantity that changes as the curve changes, okay? So this is somehow the Laplace-Beltrami operator in some respect with respect to arc length, okay? So it's that. But luckily for us today, because we will be studying convex curves, and that was the basic idea behind the Gates-Hamilton result, is that in the case where we have a convex curve, we can parameterize, we can parameterize in terms of arc length, in terms of theta, and I will explain what theta is, more or less is the angle theta. So let's say that you have a convex curve, okay, and evolving or a curve which is solution convex curve, but anyway, for any convex curve it works, particularly for our solution. So let's say here is the x-axis on the plane, right? And here is the x-axis. There's x and y, right? And this is the y. Doesn't matter, but okay. Now, at each point, you have the tangent, right, vector, or the tangent vector to the curve, okay, which forms a line, right, which forms an angle theta with the x-axis, okay? And because you have a closed curve, right, there is and convex, there is one-to-one correspondence between the tangent vectors and the angles. And because of convexity, and because it's closed, as you go around the curve, you go from 0 to 2 pi, right? And so therefore, you can parameterize, so theta goes from 0 to 2 pi, and you can express kappa, the curvature, as a function of theta and t, because for every point you assign a theta, at every point you have a curvature, and it's one-to-one correspondence, and you end up with a beautiful PDE, which I write here. Let me write here. Kappa t is kappa square kappa theta theta plus kappa cube. So kappa square appears in this. And now this theta is on 0 to pi. And of course, if you go around the curve, if you go twice around, you pick up the same curvature. So it's a periodic. Kappa is 2 pi periodic. In this parameterization, And because you have just a curve, and because you are in 1D, all the information, right? All the information of the flow, right? It's really included in this equation. So if I want to study how many ancient solutions I have under convexity, not how many and which ones, all right? It's enough to study 2 pi periodic solutions of this very simple PDE. So it's right. It's a mildly nonlinear PDE. Okay. So the problem is not difficult. Now it turns out, because of this has a kappa squared. When you do calculation, it's much handier to have a kappa, like it cannot be kappa, but a p, to be linear, right? To have exponent 1. Of course, the kappa has exponent 2. So the natural quantity to introduce is the so-called pressure. The name pressure comes because we introduce this quantity in the so-called porous medium equation, which describes describes the pressure of the gas through a porous medium. So anyway, so we introduce P to be kappa squared, right? So it's the square of, and then you compute the evolution equation of P in terms of the evolution equation of kappa. And it turns out that P satisfies this nice, again, evolution equation, and we will be working with this. So soon I'm going to switch, I'm going to switch just to board. Okay, so let me write it. So P is kappa squared, and P sub T is P theta theta minus 1/2 P theta squared plus 2, I think. Is it 2? Do I have a 2? Yes. Plus 2 P squared. Okay? All right. So, and now we should keep something in mind, that kappa sub T is non-negative on an ancient solution. And that would play an important role in our proof, which I will state later, which implies, of course, that P sub T is non-negative. And just one word, how do you obtain such a result? And I don't want, again, it's if you're not familiar at all with these equations, it's okay. But for the students that are a little bit more familiar, so Richard Hamilton. Remember, in our first class, we talked about these differentiable inequalities. Okay, the one that you even tried to prove with Robin, right? So this is very similar to those that we tried we did in our first class, but a little different, and it's proved by Richard Hamilton. It says that for any curve, that happens for any curve evolving by curve shortening flow, compact curve, closed curve, let's say it starts at time t naught, okay, with starting at t naught. T naught can be 0, 100, or minus 2000, all right? I can start at any time I want. I can start, and then, of course, I can set my initial time to be any time. It satisfies this, the kappa, the curvature, satisfies this equation. Okay? And now what happens? So this, if I bring this to the left-hand side, this is a non-negative quantity. And now what happens if I let T naught on an ancient solution? I can let T naught go to minus infinity. And if I let T naught go to minus infinity, right? And I know that this is bounded, and it will be bounded at minus infinity. This will be going to 0. No, sorry, it's bounded at a certain, it's uniformly bounded, but it's bounded at a fixed point, because T naught, you see, T naught is the initial time, right? And then, and the kappa is for any fixed time, right? So I have kappa T I have kappa t is plus kappa 2t minus t naught. So this is at the point, let's say, s and t, minus kappa s squared over kappa squared. Let's see, my scaling kappa. So bigger than equal to 0. And now t naught, this happens for all t bigger than equal than t naught. But on an ancient solution, t naught can be as negative as I want. All right? So I can let t naught, which is my initial time, go to infinity, and this disappears. And that eventually gives you this, which is independent. Okay. So this we will be using. All right. And so now, before I switch to the board, let me just give you, so there are only two examples that we can think of ancient solutions, ancient convex solutions that we know explicitly. The one we talked about is the circles. All right, if you have circles that they contract, they are ancient. So the basic examples here is the circles, so which are independent solutions. So P okay, they're solutions that they depend only on time. The curvature of a circle is constant in space, right? Right? So the curvature depends only on time, and this capital T is the time where the circle will contract to a point, therefore its curvature will go to infinity. All right? So this is. Now there are other solutions that they were discovered by Sigurd Angenent, the person who gave you the computer session yesterday, who look like, okay, he calls them the paper clips, and this is a normalized picture. This tells you somehow that very far away to minus infinity, they look like two lines here, and here they are compact. And this solution, there exists a solution which exactly looks like that, and this is the so-called Grim Reaper solution, that's how they call it. And this is a translating solution, non-compact solutions, all right? But we're talking about compact solutions, so these compact ancient solutions, they look more or less one Grim Reaper, another Grim Reaper glued together. And that's the picture close to minus infinity. As you go forward, it changes, of course. These guys move to inwards, and then eventually you become circular. Now, you become circular as you contract to a point, but since he wanted, I took it from Sigurd, he wanted to show us how it does. He normalized a little bit the length, okay? And the theorem that we proved with Hamilton and Celsum back in 2010, that these are the only closed means compact, convex solutions to the curve shortening flow. Okay? All right. So I have 15 minutes to tell you about the proof. Okay? And the proof really relies on studying these 2 pi ancient periodic solutions of this PDE.
Are you assuming embeddedness in the theorem?
Everything is embedded here. You have? Yes. Everything is embedded, otherwise nothing of this works. You have many more weird stuff. Okay, let's see. I don't have so much time. I'm always behind, but okay. So I will use a little bit more of this. And then, yes, question?
Oh, sorry.
Okay, all right, okay. So let me clean up a little bit this, first of all. So I have an ancient solution of this equation. And let me assume that ancient, of course, means that I am from minus infinity less than t, and let's assume that this capital T that I have there, where the solution shrinks to the point, I take it to be 0, so that I don't have to write it. So it's less than 0. Okay? So that's less than 0. And P is 2 pi periodic. Since I am convex, P, anyway, P is kappa squared, so P is always positive. And I know that now P sub T is always positive and smooth. Okay? And I want to show that the only two possibilities are these two examples. Okay? All right. So the proof comes simply by playing with monotone quantities, as we say, Lyapunov functionals in PDE. So you introduce a alpha, which is P sub theta, and you differentiate through this equation, and actually it turns out if you differentiate, there is some cancellation here between this term and when you throw the derivative here. So the equation for alpha, which is P sub theta, it's even much simpler. So alpha satisfies alpha sub T is P alpha theta theta plus 4 alpha. Is this. Okay? All right. So this is a very simple, this is almost like a heat equation, okay? A very simple parabolic equation where you can really view this as a coefficient. Of course, in this case, it's a nonlinear equation because there is a dependence, but I can also view it like that. Okay? And there is, so I define a very simple monotone integral, all right? This, which will play the role of our Lyapunov functional, I of alpha to be this. And you may say, how did you find this? Usually, you remember, I don't know, we didn't talk so much about calculus of variations here, etc. But you see, in a parabolic equation, this alpha, right, in the heat equation or Laplace's equation, this alpha theta squared, the integral plays the role of the energy. All right? So this is more or less the energy. This comes just so that the arithmetic works. So this part comes so that the arithmetic works, and this is the natural thing to consider. Okay? So this is our magic quantity, and I'm not going to do this calculation because unfortunately I don't have time, but it's, or maybe I can, all right, I can do it, or let me continue with the proof, and if I have time, I'll do it at the end. So this is minus the integral from 0 to 2 pi alpha t squared over p d theta. How do you prove something like that? I will try to show it at the end, but if I don't have time, you do the ddt of this, right? And then, okay, this is a lower important term, but this one gives you 2 alpha theta t. You integrate by parts in theta. But if I have time, I will give you the calculation. But it's a straightforward calculation. By the way, I will post notes as well, so you can see the calculation yourself. But if I have the time, I will do it. Okay, so this is a very standard calculation with this equation. So this is nothing. So we know that we have a nice monotone quantity. Okay, all right. And and the next step is to show So the proposition, the basic proposition is to show that A of alpha of t on an ancient solution is identically equal to 0 for all t. And I will try to show you how we show this. But, all right? Okay. So this is the main proposition. So let me first show you why once you have this, you can classify the solutions, and then I will just show you how you go about showing this. Okay? All right. You see, okay, once you have this, this implies, right, that d dt, if this is true, then you have d dt of A of alpha of t is identically equal to 0, of course, because the derivative of 0 is 0. But what do we know? We know that this is equal to this. So if this is identically equal to 0, this is identically equal to 0. Okay? And once this is identically equal to 0, all this is non-negative, alpha sub t is identically equal to 0. Very well, because what does this tell me? This tells me that alpha sub t is 0, p is a common factor, is positive. This means alpha theta theta plus 4 alpha is 0 for every t. Right? Okay? And once you know that, then, okay, you can solve, everybody can solve the second order PD. You do a combination of sine and cosines. The only difference is that the coefficients here depend on t, because for each t you solve, okay, I don't have it, I can write it. Let me just see so that I don't make a mistake in the calculation. Here, alpha theta t is going to be some alpha naught of t cosine 2 theta plus gamma naught of t. Gamma, because you see these are, you can always, and then b naught, beta naught of t multiplied by sine of 2 theta plus gamma naught of t. Okay? This is alpha, which is p sub theta. Okay? And now if you integrate in theta, you end up with p, which is the square root of p is kappa squared. All right? So I'm going to, p of theta t gives you some other combination of sine and cosines, alpha of t, etc., plus beta of t, all right, cosine sine, similar, I don't, okay, plus some constant, because, right, it's the derivative. And now, if this alpha of t cosine, sine here, plus beta of t cosine, if this beta and alpha is identically equal to 0, they can be anything, then this means that I have only p of theta t is c of t, so I recover the circles. Okay? Otherwise, if it's not, I just plug it back to the equation and I deduce that, okay, if not, right? So from that I deduce that p is either 1 over 2 minus t, p of t, or p of theta and t is the formula that gives the it's a straightforward calculation. It could have been an ODE problem where nothing now, the constants lambda and gamma are fixed. The reason is because you have alpha sub t is equal to 0. That's a very strong condition. So you don't expect this coefficient here to depend on t. Okay? I don't have so much time to show it. This is very straightforward. Once you have this, then you know how to find the solution. So, all right. So the key part, therefore, is to show that, right, that I of alpha is identically equal to 0. Okay? So we have introduced this monotone quantity. We know that our quantity, so monotone, therefore d I of alpha of t over dt, we know that this is less than equal to 0. And we want to show that it's identically equal to 0. Okay? All right. And this is done by two steps. Right? So how is it done? You look at how it happens at minus infinity, and you look what happens at 0. Okay, let's first look at 0. The limit as t approaches 0 of alpha of t, we show that this is equal to 0. And remember, what is 0? 0 times 0 means my solution becomes circular. What does it mean circular? Means that the derivative of my curvature is equal to 0. Because, okay, if it's circle, means I have curvature the same everywhere. So then kappa sub theta in the right scaling is 0, which means p sub theta is 0, which means alpha is 0. So if alpha is 0, I of alpha is 0. Because alpha is alpha, the I of alpha just depends on alpha. So this follows from the Gates and Hamilton. Actually, we need, I'm cheating a little bit because it's not exactly what I say, but the idea is this, all right? So this follows from the Gates and Hamilton result, which says that as t approaches 0, the solution becomes circular. Right? I wrote on my board because I didn't want. Okay, so now the only point, the only thing, so the more interesting part, which I will take 2 minutes. I still have 3 minutes. Okay, very well. The most interesting result, because where we use that the solution is ancient, is that the limb inf as t approaches minus infinity of I of alpha of t, it's less than equal to, is bigger than equal to 0. This is the key step, all right? So this is the key step to prove the proposition. Okay? But let's think first. Let's say we know this, okay? We have what is the proposition? The proposition says that this is identically equal to 0. If we know this, then you know that at minus infinity, this is positive. The limit is positive, it is positive. It decreases, sorry, this has to be negative, sorry. Wrong. It's negative, it's less than equal to 0. Okay? Because it decreases, and then it becomes 0. Therefore, it has to be identically equal to 0. So the key step is to show the limb inf of this. And now, okay, I don't have time to write down the whole proof, but I have time to show you a little bit on the slides. Okay? So the key step is, again, to prove that this is less than equal to 0. So how does the proof go? The proof, okay, again, it's not difficult. It's here. The idea is to introduce another integral. This is, we call it like the second whatever. So this is a second, so you introduce this integral, the p theta square over the integral of p theta square over 2p. So you introduce another integral so that d dt of your integral is the thing you want to show equal to 0. All right? Okay, so right, let's don't worry right now, just want to do the idea. This is a very standard procedure. The people use all these ideas when they look at asymptotic behavior of solutions at infinity. This is very similar idea. Okay, so you introduce this new energy, p theta squared over 2p, and you show that the d dt of this is minus alpha of t. And now let me just take this and show you, just by integrating from minus infinity, how you end up with what you want. All right? Okay, so you look at d dt, I'll take one, the integral from 0 to 2 pi, p theta squared over p d theta. This is minus I of alpha of t. Okay? And now I'm going to integrate from minus infinity to a fixed point t naught, from minus infinity to t naught dt, and then dt. All right? So I took this and I integrated with respect to t from minus infinity. Okay? Now, t naught, I want to put any number less than 0. Doesn't matter. You can take minus 100. I don't care, because I only want to look what happens at minus infinity. Okay, let's do this. Here you do the integration. So what is this? This is the integral from 0 to 2 pi p theta squared over p at t naught d theta minus the integral minus the limit. Okay, let's say that the limit exists. It may not exist, but otherwise you do some lim sup to bound it. But let's say it exists to make things simple. The integral from 0 to 2 pi p theta squared over p at minus infinity d theta. Okay? So this is the left-hand side. And the right-hand side is minus the integral from minus infinity to t naught I of alpha of t dt. So this comes from just integrating in t this inequality. And now, of course, you may ask me, the key point here is that so in other words, the integral from minus infinity to t naught I of alpha of t dt is equal to minus this plus this. So it's equal to lim as t approaches minus the integral from 0 to 2 pi p theta squared over p. Okay, I put this is a t because I took the limit outside. D theta minus, this is a constant. I don't care what it is. The important part is that this is bounded. And that follows from using Hamilton's estimate. This follows from the fact that this is bigger than or equal to 0 and you in some integration, but I don't want to get into it. And now, okay, since we know that this is bounded, we don't know really that this is non-negative, but let's assume that it was non-negative. I just want to show you the idea. You have something that it's integrated all the way to minus infinity, and you have a bounded integral, right? So then you have that the limit has to be 0. Now, since you don't know that that this is positive, you know that the lim inf has to be less than or equal to 0, because if the lim inf is positive, then you get something that blows up. So this implies that the lim inf as t approaches minus infinity of I of alpha of t is less than or equal to 0, and we are done. Okay, sorry I ran a little bit out. Okay, so it's a simple proof, very simple proof, and as we're going to see next time from the Ricci flow, is that life is not so simple there, but at least that was, I hope I convinced you that was not so difficult. And I will give you notes, so if you want to study the details of the proof, it will be in the notes.